We're live. Okay. Hi, everybody, and welcome to the Education Showcase 2022, formerly seen at PyCon AU. This is the I Can't Believe It's Not PyCon edition. Welcome here today. I'm Renee Noble, and I'm the Regional Cloud Advocate for Australia and New Zealand. What that means is I get to teach people about technology and education and Microsoft stuff, but also general coding, and have fun workshops and sessions like this. And we're super excited to be here today with Tech Inclusion, something I'm also part of, but I'm wearing too many hats today, so it doesn't make any sense. You're going to see me even present later on a different thing. It's going to be very confusing. I'm going to hand over in a second to our lovely Tech Inclusion host for today. But firstly, I'm going to say we're here. So these are our lovely hosts. We've also got, firstly, we've got Amanda on the far side from me, amazing teacher and former Microsoftie and educator extraordinaire is what I would say. We've got Alex McCulloch here. She's a superstar at Atlassian, and also the Chief Operations Officer at Tech Inclusion, and our leader of many things at the Girls Programming Network, including Girls Programming Network Sydney, coming soon again after COVID. It will be back. Online, we've got Nikki Ringland. She'll be answering questions in the chat and gathering any cool questions for us that we might want to have announced over. She'll be the voice of God coming down from above. We do have a 7-second delay if you are online, so that might be a little bit funny later on, but if you do have questions for anybody and you're at home, do put them in the chat and Nikki will be able to read them out if you've already had them in 7 seconds in advance, so that would be great. And I'm me, I already said that, but firstly, I do want to acknowledge that we're here on Gadigal land, the Gadigal land of the Eora Nation, and we pay respects to elders past and present. And do drop in the chat if you are online, if you're gathering from another Indigenous land, whether you're in Australia or overseas. Let us know. In a second, we're going to move on to the student showcase. But first, we need to hand over to our amazing hosts. So that's all you. I went too far on the slides. Over to you.
We have a couple of special guest speakers. We've got Renee Noble here. We also have Alex Hope online. And then we have 7 amazing talks that are pre-recorded for us today so that we can watch what the amazing students all over New South Wales and the ACT are doing with Python. And so it's going to be a pretty great evening, I think.
Yeah, it's going to be great.
Yeah.
Cool. So I think we can get started with our first intro of our first talk.
Yes.
Great. So first up, we have Jack, who's
we've got Alex first.
We've got Alex.
Oh, I'm so sorry.
Exactly...
Alex is first.
Can't jump the gun.
We have Alex first. I don't think I have an intro for Alex.
And we're also going to need Alex to share their slides in the screen share place.
If you'd like, I can give Alex an intro.
Go for it, Nikki.
Fantastic. Thank you, Nikki.
There we go. All right, so hopefully this is not echoing too badly. Alex does cybersecurity at Atlassian, committing cybercrimes and then writing very, very detailed confession letters. They're known for one time using Inspect Element to find the passport number of former Australian Prime Minister Tony Abbott, and inadvertently thereby entering into the Do Not Get Arrested challenge. You can read more about that at HPS mango.pdf.zone. I will drop that link in the chat as well. And generally, I should say that Alex supplied this bio. They have no idea what they're doing, but are happy to be here. And we are very, very happy that you are here, Alex.
Thanks, Nikki. I'm so sorry. I did not realize that someone was going to read that out, but I guess that's happened now. I just wanted to tell you all about a little thing that happened to me. I was kind of jealous that everyone was showing off their cool projects today, so I wanted to do it too. Is everyone seeing the slides? Just kidding. You're not going to be able to reply for 7 seconds, so don't worry about it. I hope you can. My name is Alex, but you can call me Alex in double quotes. You may be wondering why the double quotes? What's the deal with that? It's very simple. A few years ago, a couple of journalists wrote about me, and they referred to me in their articles as a hacker who goes by the name Alex in double quotes. And that's Alex is also my real name, as you all just heard. So this is my hacker name now, I guess. I know Nikki just read a bio about me, but quickly here's a little bit more bio. Like we heard, yep, I work at Atlassian doing security there, and I wanted to be more specific. I said that I write detailed confession letters. I do hacking. What do I actually mean by that? It's very simple. There are 3 steps. My job is to hack into Atlassian exactly like a real hacker would, or exactly like we think a real hacker would, and then share everything that happened with Atlassian because the real hacker wouldn't tell you what you missed, and then finally sell the stolen data on the dark web for big money. We don't actually do that part. Not really. That's just made up. That's just fun. I should say though, one time I did this exact slide and the big X didn't come up. It was really bad, but I reassured people that it would come in. But enough about me. I wanted to tell you the story of, I think this is the first talk. This is the first talk I did ever about a project. So here's my school project. I totally was finished school by the time I did this. One day I was browsing this website right here. This is a website called Facebook.com. If you don't know Facebook, it's a website where you can watch boomer society collapse in real time. Specifically, I was looking on the side here at this little sidebar thing, and I was like, what's the deal with these green dots? There's all these green dots next to people, and their little number tells you something, 18 minutes. And I was like, what are these green dots about? They're telling you, oh, this person's online, this person's not online, or this person was online 18 minutes ago. But I was thinking, how do the little green dots work? How does it know whether there's a green dot there? How does my computer know whether my friend is online or not? And so I decided I wanted to figure that out using hacking. And there's only one hacking technology or one hacking technique that I knew, and I wanted to show you that same hacking technique today. Step 1 is to use right click. And to show you step 2, I've prepared a short video, which maybe we'll play now. I hope that answers everybody's questions about hacking. Just in case nobody's seen that, someone hasn't seen this before. This is not actually hacking. This is just right-clicking in Google Chrome. If you're at home, you can do it right now. And you click Inspect Element, and it opens up this view thingy at the bottom, which shows you the HTML representation of the page you already saw. Just once again, want to stress this is not hacking in any way. This is just a normal way of seeing the same information that's already on your computer. Which is why I found it so surprising that as soon as I did this, Facebook gave me this big warning saying, hey, careful, don't do hacking, stop. Maybe you're doing too much hacking, or maybe someone's tricking you into hacking or whatever. And I was like, don't worry, Facebook, I know what I'm doing. And so I looked around and I clicked around in there and I saw this page, which shows you the list of everything that's being sent to your computer. And I was like, I eventually ended up looking at this pull thing. And I clicked it and it showed me this, which was a whole bunch of something, and I didn't really know what it was. And I had a fun time trying to reverse engineer what this is, figure out what this means. And I thought it'd be fun if we could all do it together. I guess I can't actually hear your answer in real time, so it's a shame. I was going to ask you all to do it, but I guess I'll just explain it to you. It's a bit tragic. I mean, maybe Nikki can do it. That's no fun.
That's a lot of pressure on me, Adam.
Yeah, all right. I decided not to make Nikki do it. So the first thing I saw was this thing. And I was like, well, this is probably, it's like T message. This is maybe the message type. Yeah, I'm going to say it's message type. And the next thing was the sequence 4 thing. And I think, yeah, that was like a sequence number of something. I don't know what's the sequence in. I don't know why we need sequence numbers, but I thought that's probably some sequence number. I don't need to know about this. This next thing I thought was more interesting because it said U in front of it. And I was like, well, what could U be short for? Probably U is short for user. And I was like, well, I don't know anyone named that number, but I think this is like someone's user ID. But eventually I figured out this is my user ID. So I was like, okay, Facebook's sending me my user ID. I don't really need to know that. But then it was showing me this other thing and this overlay thing. What's this other number? And I was like, well, that kind of looks like the same number of digits as my user ID. This is probably my friend's user ID. And so it's telling me for each little green dot which friend it belongs to. And then I saw this thing, which is called LA. And I was like, Los Angeles? No, that can't be right. I didn't know what it was, but I knew that this happened to, if you spend too much time looking at computers, you eventually learn that numbers that look like that and start with 14 or actually 15 now are timestamps. And so this is a different way of storing a date and time. But what this is telling me is this is the date and time down to the second that this person was last online on Facebook, whatever that is. And this is the part that's going to end up being important later, I promise. Then next, does anybody know what this stuff is? I also don't know what this is. I still never figured out what this is supposed to be, but I guess it wasn't important. Moving on, professional hacking. The next thing I found was this thing, which is some some sort of JSON, some sort of JavaScript thing, and it's giving me my friend's user ID, and it's showing me what status they are. So status means you're not just online or offline. I have other statuses. It has like, am I online? Am I idle? Am I hiding? Am I invisible? Am I fully offline? So it tells you which one of those are. And it also tells you for like, it doesn't just tell you whether they're online or not. It tells you, are they online on their computer? Are they online on their phone? Are they using the Facebook app? Are they using the Messenger app? And there's a different status for all of those. And it's all being sent to me. And when I saw this, after just innocently clicking around in my browser, I was like, well, I guess that's not that strange that I can see all this information. I mean, I can see when my friends are online by looking at the green dots. But I was like, well, what if, I mean, I'm looking at the green dots now, but I'm not always looking at them. What if there was somebody who was always watching those green dots, like all the time? I wonder if there'd be any pattern there. And so I wrote a whole bunch of code to do exactly that. To Facebook, I wrote a whole bunch of Python to like automatically be logged into my Facebook account and like check like every 1 second which people are online and what their status is. And it ended up looking like this. So for every person, there's a file, and in that file there's the time, and it says what status they are on everything in that time. And actually I ended up making a lot of these files, one for every Facebook friend I had. And I was like, wow, now I've downloaded all this data. This is great. I love being a government and spying on people. This is fun. But I can't read this. I don't really understand what these numbers mean. I can't really kind of look at this and learn anything. And so I decided that actually I should try and make a graph out of this, because maybe a graph would be like easier to understand than just looking at the numbers. And then I used programming to make a graph, and it ended up looking like this. I'm going to save you all that programming because it was a big mess. So here's what one of those files looks like in graph form. And so I thought it'd be fun if we could kind of all analyze those together. These are real files, are real Facebook friends who've consented to having their information put in here anonymously. And I wonder what we could find if we were always watching those little green dots on Facebook or really any other website that does this. So just to show you what we're looking at here, down the bottom here, we have the time. It's really small, but I'll read them to you, don't worry. And on the left-hand side, you have how online the person is. People can be more or less online. At the very top means they're active. If they're in the middle, it's idle. And otherwise, below that, they're different kind of offline. And at the different colors mean which device they're online on. The dark blue one is just generally online, and the other colors are different devices. So for example, the orange one is the Messenger app, and the lighter orange one is the Facebook app, and so on. But this thing that you're seeing now is just like a little sort of 30-minute window of somebody's like online time. And you can see that, they're offline for a while, and then they go online on and off for a while. Okay, so what? The problem is, because you can write code to be always watching these little green dots, you can zoom out on this. You can zoom out even more. So here's the same person, but now it's zoomed out. So this is over 12 hours, I think, or something like that, almost 12 hours. And so, there's a lot of information there, but you can generally see there's a bunch of stuff happening, and then there's nothing, and there's a bunch of stuff happening again. And I realized, well, what could that be? What could that nothing time be? I looked at the times, and I was like, oh, the time when nothing's happening is between 12 a.m. and 9 a.m. And I was thinking, oh, this is like telling me roughly when my friends are asleep. That's kind of like creepy that people can see that about you, and that I can see that about them. I don't really want to be able to see that. And it's not actually telling you when they're asleep or not. It's just telling you when they're offline online on Facebook. But it's pretty hard to be online when you're asleep. But you can keep going and zoom out even more. And eventually you can start seeing patterns like this, where there's people who are online. This is now zoomed out to over a couple of days. And you can see people are online for a while, and then there's a gap when they're not online, and then they're online for a while, and there's another gap, and those gaps tend to be at nighttime. And you're like, wow, this is what it would be like working for this is what it would be like if I was like part of the, dystopian government surveillance thing. I'd be able to like watch this about all my citizens. Jeez. I was like, it's kind of yikes that this happens on Facebook, right? It's kind of a lot that like your friends can just see this about you. And like, it's not just Facebook, it's any website that has like online or offline green dots. You could just write code that keeps checking the green dots. And this was sort of my first time like trying to like actually do hacking or trying to understand computers or trying out something weird like this. And I ended up finding this strange, creepy thing. And I was like, oh no, I think it probably shouldn't be like this, but also there's nothing you can really do about that. So here we are at yikes. But if you're worried about this, don't be, because this doesn't work anymore. I think it doesn't work as well anymore because of the way Facebook works. Or actually, maybe it does work the same. I don't know. I haven't actually tried it in a long time. So yeah, if you like this talk, then you might also like this website. Maybe this is a website for you. Maybe you'll enjoy it. And in conclusion, please do not do crimes. Yeah, the end. If you have any questions, I will be reading the chat. But otherwise, thank you very much.
Yeah, do we have any questions in the chat, Nikki?
We have to wait 7 seconds.
We do.
Or people need to be prescient.
Yeah, does anyone in the room have a question for Alex?
The Python language and using HTML makeup language use scripting Facebook.
Do you want to pass the handheld? We actually have a roving mic as well.
Yay, I love questions. Maybe I should bring the slides back.
Nice to meet you, Alex. It's a nice name. May I
Thank
ask,
you.
is that using Python language plus the makeup HTML to script in Facebook? And for your visualization, what is your time sliding technique in your Python language for awake and sleep? What this means in cybersecurity?
So I think there was a couple questions there. Am I using Python to actually download the
Yeah,
information?
sorry, a
from Facebook?
breakdown to smaller pieces to answer, please. Thank you.
Yeah, it's okay. I can do it. What am I using to actually download the data from? Oh, sorry.
Take it away, Alex.
Okay, sorry. I can't see what's happening. So yeah. Yeah, I was using Python to actually download the information from Facebook to like log into it and be checking the green dots all the time. But to actually make the graphs, I skipped it in the talk, but I was using this JavaScript thing called d3.js, which I actually tried a lot of different graphing libraries and they were all quite bad. Even at the end, the graph I had was kind of dodgy, but I eventually gave up and stopped thinking about graphs and just used some mediocre JavaScript one.
Any other questions? Anyone signing up for the NSA now? Careers? Anyone at home currently on that? No. Alex said don't do crimes.
We do have a question from the internet. Griffle, I'm not sure, asks, what counts as crimes?
Hey, thank you so much, Griffol, for asking. I personally couldn't possibly know that because I've never done a crime, but thank you so much for asking.
Excellent. Clear as anything. Whatever they are, just don't do them. Good. Excellent. Yes. If it's possible, is it possible to point the camera at the audience for questions? I'm not sure if the camera is actually mounted to the ceiling, which may prove challenging.
It is very much mounted to the ceiling.
In the sky.
I'm not sure if anyone's tall enough to. Yeah. Okay. We like that corner. It's a good corner. It's a good corner. Cool.
Any other questions, Nikki?
No, some more reiteration that do not do crimes is good life advice. That's about it for now. I believe Alex is available, accessible to answer more crimes-related questions on Twitter as well, and possibly in the chat afterwards.
Great.
Okay, I will rearrange the screens for our in-room things.
No longer blocking things.
No longer blocking things. Good cooperating members of society.
While you're getting things up, there is a counterpoint of do crimes. Just in fairness, I feel like we should see all sides of the story. So.
Balance is important.
Balance is important.
Yeah.
How are we going with the slides?
Yeah, well, we need the next. Oh yes, we need to click this one. I'm all on board.
You've got it, Renee.
I'm great at slides.
You're doing so well.
There we go.
Okay, great.
Okay.
We're doing it. So first up, we have Jack, who's been programming for 4 years. This is his favorite emoji. Very cool. He recently learned that while Python is an interpreted language, there's still a compilation step, with the Python getting compiled to bytecode, which is in self-interpreted. Very cool. So Jack is going to be discussing Mandelbrot set generation, which will be very interesting. We'll go over there.
Yeah.
And we'll play video 1.
Yeah.
Hopefully.
I need to. This one back here, I think.
Hi, I'm Jack, and this is my Year 12 major project. It's a Mandelbrot set generator designed to explore the infinite unknown of this dazzling fractal. For anyone who's not familiar with what the Mandelbrot set is, it's a famous fractal in mathematics that shows up through iterating numbers through a certain function and plotting how they behave with different colors. These numbers are complex numbers, however, I find it easier to just think of them as a point on a 2D plane with an x and a y coordinate. Part of what drew me to this project is my fascination with chaos, and how through simple iteration, the Mandelbrot set creates such crazy, chaotic, yet self-similar patterns. My inspiration for this project came from my math class.
It is. It's just really quiet. Yeah.
Having some audio technical difficulties.
Yes.
Yeah, we can hear it. It's just quite quietly. How is it online? Also quiet?
Yeah, I turned up to the maths.
It's certainly audible, but I have better volume control from this end as well, so I'm not sure.
Yeah, that'd be great. Thank you, Sarah.
Thanks, Sarah.
The magic of hybrid events. We're still learning, I think, but we're getting there.
Online, say it's fine.
Thank you, online squad.
Where we were learning about the fractal, and we were given a two-dimensional grid of about 5 by 5 and had to do each calculation of the 25 points by hand, which is great for our arithmetic, but incredibly slow and unsatisfying. So obviously we also looked up some high-resolution images online, but at this point I was already thinking of how I could use Python to write a program automating all this math and displaying it in a bunch of cool ways. So when you launch the program, this is the starting screen that you're greeted with. And there are 4 main things to interact with here. So you have the Mandelbrot set in front of you, which in this instance is red. And up the top left, you have the input for the file name. So when you're generating new images of the set, they are distinguished from each other and won't override each other. Now, so I'm just going to set this as test. Up the top right, there's instructions, brief instructions that just give you an overview of what everything does, but I can explain it to you. Down the bottom right, there's this zoom lock, and it says it's on. This is a feature that I implemented because you don't want to use to click multiple times because it'll crash the program. So essentially, what you do to zoom in on the set is literally just click on a part that you find interesting. So say if we want to zoom in on this very end point here, you click the space bar to turn the zoom lock off, and now you can see in the bottom right it says it's ready, and then you click on that point that you want to go to, and then this box will come up and say it's generating, and the program has stopped responding because of the recording software, but that's okay. It should still work. Yeah, so there we go. So now the instruction box is gone because that was just on the starting screen, but now we have a much more detailed view of the point, a much more detailed view centered around the point that we clicked on. So yeah, and now essentially you can just repeat that process again. So again, we have to press spacebar to turn the zoom lock off, and then we click where we want to go, and it will keep on zooming in like this, centered around the point that you clicked on, and you can get a
Get Nikki to share her screen?
Yes. We're going to get Nikki to take over, just so maybe we can hear in the room, because we did come in and with the hopes of both pizza
And audio.
yeah.
Both.
Okay. What was that?
We get a round of applause for the great audio and visual work in that video.
It might be terrific. We just can't hear
We
it.
just can't hear it.
It's just not coming through. Okay. We're getting Nikki to share her screen. So then maybe we'll get better audio coming through StreamYard in another direction.
Is anyone here good with computers?
Anybody? Anyone a professional software engineer or
I wouldn't know anything about this.
No? No one works at a big tech company? Or,
I don't know anyone.
Shucks. Who'd have
No.
thought in a room like this? Anyway, Nikki's
alright.
gonna be our room screen sharer, and hopefully it's gonna be amazing. Otherwise, we'll do some stuff.
I haven't shared via StreamYard before. If we
Yes,
can.
you're gonna need to share a tab. This is
Okay.
a
All right. I was
introductory
trying the
lesson to
advanced
StreamYard
option.
now.
The advanced option was not the goer. Folks online, you should share your snack preference right now.
Yeah. Let's hear some snacks. Ooh.
I know someone. I believe Daisy was going to go get ice cream.
That sounds great.
Where is
It's
it?
lost
I just want to
Nikki.
make the people with pizza feel jealous.
Yeah.
Good.
Go
I
on.
was hosting a workshop earlier today, and someone
Hi,
was like,
I'm
"There's
Jack, and this is my Year 12 major project. It's a Mandelbrot set generator designed to explore the infinite unknown of this dazzling fractal.
Is that audible?
For anyone who's not familiar
It's
with what the
very
Mandelbrot
quiet
set is,
still.
it's a famous
We have
fractal
some
of
loudness,
mathematics
Nikki?
that shows up through iterating numbers through a certain function and plotting how they behave with different
Not
numbers.
through that fashion. That's
These
at
numbers are
max for
complex
now.
numbers. However,
Let me click some buttons in StreamYard and see if there's some sort of magical thing in settings. There's not. Cool. This has been useless divergences from Renee.
Could it be the echo stopper thingy?
Maybe. I think that I'm of turning this off. There is. It's on maximum. Is it just this video that might be really quiet? Amanda and Nikki, who went through the videos.
They were all mostly okay. I didn't notice this one was particularly quiet.
Yeah, let me do a thing. Let's try one more thing.
Let me try sharing it via Chrome tab as well.
Did you not do that? I didn't know.
No, this was sharing that was sharing the video directly.
Oh, well, that's also good. Okay, let's do one more thing. Maybe I can play the video and we'll just have to do a bit more herky-jerky stuff.
and how through simple iteration,
Is
the
this-
Mandelbrot set
is this one
creates such
audible?
crazy, chaotic, yet self-similar
If anything, it's quieter.
My
Yes.
inspiration for this project came
Let
from
me-
No!
where we were
You moved the needle, but it went the wrong way.
shows up through iterating
Okay, maybe.
through a certain function.
1 second, everybody. Yeah.
I have a terrible idea. It's a
Great.
terrible
Do
idea.
tell us, Nikki.
I can run it through my laptop speaker and put the sound all
No.
the way up.
No. Okay, let's do. No, because I can't. Okay. Let me make this have the correct audio output, and maybe.
It's the same.
It's still
We
really
could get
quiet.
the in-person audience to just gather around the podium. It won't help,
Let's
but
just
it'll make us
have
feel
a
better.
flash forward sneak preview of the next one to see if it's just that audio on that video. Is that
It's still-
fine?
it's better, but it's still quiet.
To just think of them as a point on a 2D plane with an
Oh,
X and
boy.
a Y coordinate. Part of what drew me to this project is my fascination with chaos and how through
Yeah.
simple iteration, the Mandelbrot
one's
set creates
quiet.
such crazy, chaotic, yet self-similar patterns. My inspiration for this project came from my math class, where we were
Everyone in
learning
the
about
chat,
Python,
could you
and
let
we were
us
given
know
a
what your first
two-dimensional grid
programming
about 5
project
by
was?
5 and had to do each
Okay,
calculation
that was
for
loud.
25
What was
points
that?
by
That's
hand, which is
Zach
great for
Draper and
arithmetic,
Oliver
but
Waldorf.
incredibly
They're
slow
going to be
and
loud, everybody.
unsatisfying.
So
So
I think
obviously
it's
we
just,
also
I
looked
don't
up
know,
some high
it's just
resolution
the
images
audio
online, but at this
of
point
the
I was
videos, I
already
think.
thinking of how I could use Python to
Yeah. Yep, we could do that. Yeah, let's make it happen.
Nikki just to put Jack back on StreamYard, and we'll join the YouTube just to see if
Yep.
it's better.
Okay, yeah. Nikki, can you load Jack back up again? And we're going to join the live stream, everybody. Welcome to the in-person online event.
Hi, Renee, it's Sarah. You wouldn't believe it. We've just lost Nikki out of the studio, so she should be back shortly. She's just dropped off.
Okay. Maybe Sarah could play Jack's video again, and we will be joining the live stream. I'm just going to need to grab the link. Thank you, Amanda.
It's truly high.
This is what a career in technology is really about.
Nikki is back in the stream. Hi, Nikki.
Hello.
Hi,
I got
Nikki.
We missed you.
Apologies. So if you can try that screen share again.
All right.
Yep, we're going to join the live stream, which is coming through. Okay, and that was me 7 seconds ago. So I'm going to turn my mic off, and Nikki is going to talk, and I'm going to turn off.
It's great for arithmetic, but incredibly slow and unsatisfying. So obviously we also looked up some high resolution images online, but at this point I was already thinking of how I could use Python to write a program automating all this, displaying it in a bunch of cool ways. So when you launch the program, this is the starting screen that you're greeted with, and there are 4 main things to interact with here. So you have the Mandelbrot set in front of you, which in this instance is red. And up the top left, you have the input for the file name. So when you're generating new images of the set, they are distinguished from each other and won't override each other. Now, so I'm just going to set this as test. Up the top right, there's instructions, brief instructions that just give you an overview of what everything does, but I can explain it to you. Down the bottom right, there's this zoom lock, and it says it's on. This is a feature that I implemented because you don't want to the user to click multiple times because it will crash the program. So essentially, what you do to zoom in on the set is literally just click on a part that you find interesting. So like say if we want to zoom in on this very end point here, you click the space bar to turn the zoom lock off, and now you can see in the bottom right it says it's ready, and then you click on that point that you want to go to, and then this box will come up and say it's generating, and the program has stopped responding because of the recording software, but that's okay. It should still work. Yeah, so there we go. So now the instruction box is gone because that was just on the starting screen, but now we have a much more detailed view of the point, a much more detailed view centered around the point that we clicked on. So yeah, and now essentially you can just repeat that process again. So again, we have to press spacebar to turn the zoom lock off, and then we click where we want to go, and it will keep on zooming in like this, centered around the point that you clicked on, and you can get a much better, cooler, more detailed view of the set. Yeah, and then when you want to see these images that you looked at, so they automatically save to the location where your source code is. And so if we go here, we have Gen 0 here, which is just the initial image of the set, the starting screen. And then you can see we have test Gen 1, test Gen 2, test Gen 3, and each one of these is each zoom that we created. So here are a bunch of my favorites in a selection of different colors, and this one right here took a long time to generate because it has an approximate width of about 0.00002 on the complex plane, so it's extremely narrow. The screen is representing an extremely narrow part of the complex plane. You can also collate the images you generate in one run of the program. Since each image is from the frame of reference of the last, when you mash them together, you get these really cool animated zooms. One big issue I faced during the development of the project was translating between screen coordinates and points on the complex plane. As you can see, Pygame screens do not exist centered around 0, and the y-axis increases downwards. Adding to this issue, with each zoom, all the complex points represented on the screen change and become more precise. The solution to this issue was some well thought out functions, the mathematical kind, to translate the coordinates of a pixel on Pygame's screen into its correct corresponding complex number. This is an early prototype of my project, and it really highlights what I want to do next if I decide to keep developing the solution. The colors really mean a lot in the Mandelbrot set. Not only are they how you make stunning images like this, they also indicate how each point behaves under iteration, and there's many different ways they can do so. So there's lots of room for experimentation, which I would like to explore in the future. Furthermore, the Mandelbrot set is just one fractal made through iteration of a function. Through curiosity, I found that iterating complex numbers through other functions can also work to create new fractals. I haven't explored deeply yet, but this is a Mandelbrot-esque fractal generated with a very similar function. So that's my project. I hope you found the topic interesting. It's definitely a very cool and useful application of computing, and lots of fun to build in Python. Thank you for listening.
We did it. Look, they looked really beautiful. I'm sorry we didn't get to see the whole thing, but I think these will all be available online.
We can. I reckon we'll put it on. We can put it on again at the end.
They look really beautiful. I'm sorry we didn't get to see the whole thing, but I think these will all be available. Okay,
One second. Our weird things we don't have gone great. YouTube. No more YouTube. We did it. Okay. We've done it.
I think we're ready for our next video.
Yes. Let's find that slide. Here we go.
Resilience is a Sachs character strength. So, all right, Maria and Patrick are up next. Maria's been programming for 6 years and Patrick for 2. Their favorite emoji are the little dude with glasses and the one with the sunglasses, respectively. They've recently learnt not to carry your laptop case upside down. This is a good lesson for everyone, and not to leave the case open ever, and also learnt about containers as a substitute for virtual machines. We can watch Maria and Patrick now. Oh, Sarah, video 2.
Sarah's, oh no, yeah, Nikki.
And Nikki, video 2.
Video 2. It's over
I
here.
don't want to talk.
Hi, my name is Maria,
And I'm Patrick.
and we are part of the University of Canberra's Accelerated Pathways program, and this is a project we created for one of our assignments. We created this project because we wanted to make something cool, but also something challenging that could be useful for Australian schools. We hope that this project would serve as an inspiration for someone looking to improve pedestrian crossings.
This automated traffic light system was created for many reasons, specifically to make school crossings more efficient, less costly, safer, and easier to monitor. Currently, school crossings are either marked by signage or, in the best case scenario, monitored by a crossing supervisor. Even crossings with supervisors can be dangerous, and the supervisor has little capacity to record and store data about the crossing. Additionally, supervisors are paid by the government for what they do, which would not be necessary if automated systems were in place. This project will make crossings safer, but also record valuable data about the number of vehicles passing over the crossing and identifiable features of these vehicles in the form of number plates, should any incident occur at the crossing. According to the ABS, land transport accidents were the leading cause of injury deaths among children aged 0 to 14 in the years 2015 to 2017. 29% of these casualties occurred where the child was a pedestrian. These statistics show the importance of having well-regulated crossings for young children, especially in areas that are high traffic, such as a school zone at the end or start of a school day.
So our project is an automated traffic light designed with Arduino circuitry and a license plate reading camera. The project consists of two main components, the camera and the traffic light system itself. In order for the camera to fulfill its purpose of being a license plate reader, we had to embed a computer vision algorithm known as OCR, optical character recognition. For this project, we use OpenCV and PyTestRack to achieve the best results. OpenCV was used in pre-processing the input, images in this case, and is one of the most crucial steps when conducting OCR. When looking at the image, we can see that there is a lot of detail or noise. The computer will struggle identifying the license plate amidst all of the chaos. So we must alter the image by resizing it, applying a two-tone and bilateral filter, and implementing canny edge detection. First, we resize the image by cropping it and adjusting the resolution. We cropped it using a simple photo editing software and adjusted the resolution using OpenCV's .resize function. In this case, image cropping is super important as we want to keep OCR's focal point strictly on the license plate. Then we converted the image's color scale from multi-tone to two-toned, black and white, to make the pixel identification much easier for the OCR algorithm. Applying a bilateral filter to the image using OpenCV's .bilateral filter function puts a smoothing overlay onto it. This heavily reduces the noise while simultaneously preserving its edges, a crucial step for our next one. Now that the image is pre-processed, we can finally get onto the actual recognition part. Edge detection searches for 4 distinct edges, which in this case are the borders of the number plate. A rectangle is then formed around the located border. The image is cropped so that only the components found within the rectangle of the license plate is read through the OCR algorithm. This restricts the content that will be inputted into the OCR, ensuring much better results. Then, by calling the OCR function, we end up with this output.
Here's another example of the OCR algorithm in action. Here we took a photo of a local pedestrian crossing to reenact a scenario where the system could be used. After manipulating the image and feeding it through the OCR algorithm, this is what we ended up with.
We used a long breadboard, LED lights, 10K resistors, male-to-male jumper cables, an SR04 ultrasonic sensor, and an Arduino Uno to build the model of our traffic light system. At default, the traffic light stays green for vehicles, but as soon as motion is detected within a certain range, the light goes yellow while the pedestrian's light prepares to go green.
Just a quick note to mention, please keep in mind that this is only a model. The delays will ultimately depend on the traffic flow of wherever this system is situated.
Whilst the camera can identify and read number plates reasonably well on passing vehicles, there are a few limitations at the current stage of development regarding OCR and the camera. The camera cannot record video 24/7 as too much data would be produced to store, sort, and compute. Individual images have to be uploaded to the Python code in order for the number plate to be detected, cropped, read, and eventually output to the end user or database. Preferably, this system would be powered by a battery charged via solar panel, so that the system could be deployed to areas without pre-existing power sources. It would also be beneficial to add other capabilities to the camera that weren't possible with our technology and timeframe, such as speed detection and red light monitoring. Additionally, the OCR is not 100% accurate, sometimes displaying symbols instead of proper letters. A temporary fix to this problem would be to determine what the OCR is getting mixed up with and detecting those symbols and replacing them with letters before the data is stored into the database.
Other improvements include spending more time figuring out the most effective angle for the camera so that the OCR can run more smoothly with minimal errors. Likewise, increasing our understanding of OpenCV and PyTestRack libraries and features will enhance the project greatly, creating a more optimized system that runs 10 times better.
Whilst we have both been coding with Python for around 2 years in many different contexts such as data science and analysis or bug fixing games coded in Python, Completing this project proved to be a very challenging prospect. We were working with libraries we had never seen before, such as OpenCV and Tesseract, as well as Arduino hardware we both had no experience with. There were many ideas for additional features we could or should add to our project, like making it solar powered or adding a speed camera, but many of them were not implemented due to time restrictions and ideas that we soon realized were completely out of scope. Ideally, more time would have been spent tweaking the OCR so that there was an accurate output every single time, but the configuration options for Tesseract proved to be very complex. However, we had a really good time exploring the world of Arduino and computer vision. We hope you enjoyed listening to us talk about our project as much as we enjoyed making it.
Cool. That's awesome.
I really like their use of libraries. That was really cool.
Yeah. And I like how extendable the project is, that there's a really clear way that you could make it bigger and better next time. Cool. So up next, we have Zachary Everett. So Zachary has been programming for 2.5 years. His favorite emoji is the laughing crying face. And he's recently been learning about how backend servers work and how to make his own APIs, which is very cool. Nikki, can we pull up Zachary's? Oh, no. There we go. That's better.
Hi, I'm Zachary Everett, and today I'll be showing you my Connect 4 game and the bot that I made for it. So, who am I? At the moment, I really enjoy playing tennis. It's the main sport I play, and I have a goal of reaching Section 1. At the moment, I'm Section 2, so I'm getting there. My hobbies are programming and gaming. So when I'm not programming things, I like to play a lot of games. I started learning to program almost 3 years ago, which will be in a couple months. And I want to go to university for computer science or something computing related. And I'm currently in year 10 at a school in Melbourne. So what is my project? So I've made a Connect 4 game here that you can see in this window. So if you don't know the rules of Connect 4, each player gets a color and their goal is to get 4 in a row. So player 1 will be red and player 2 will be yellow. So they take turns and the goal is just to get 4 in a row and then they'll win the game. You can also see a bit of my code in the background here. So how have I made this? So I use the Python programming language, which I hadn't really used very much before this. I've just used it a little bit here and there. I've mostly used JavaScript and C# in the past for other projects. I use the Pygame module for the graphics, which you can see here. This window is all rendered through Pygame. I don't know if that was the best option for it, but it worked in the situation and I just used it quite a bit in the past. And also, this isn't really a tool, but an algorithm. I've used the Minimax algorithm, which is to figure out how the bot figures out what is the best possible move. So what is Minimax? So there's an official definition, which is the one I got from Wikipedia. So Minimax is a decision rule for minimizing the possible loss for a worst case scenario. And then there's my definition, which is the one I prefer, where Minimax is used for finding the best possible decision in a game where it assumes its opponent was to play perfectly. I prefer my one. The Wikipedia one might be more accurate, but I think mine's probably easier to understand and I like it more. So what I'm saying here basically is if we were to assume a game of chess, which I've got down here as a common use. So the Minimax algorithm will try to pick the best possible option by looking as many moves ahead as it can. And it's going to assume that its opponent was to play perfectly. So it won't do any little tiny, I don't know, like strategies that might make it win in a move or two. It'll try to look for the long run, what's going to have it in the best possible position, and not try to do any little tactics that might make it win in a move or two. It just wants to win by the end, and it'll try whatever it wants to just get to that point. So common uses are you could use it for chess, checkers, tic-tac-toe, or in our situation, we're using it for Connect 4. So what is Minimax? So I explained a little bit there, but this is how it actually works. So at the moment, you can see we're at this node. This will be the actual current state of our game that we're playing. So in this game, we're going to assume you can only have 2 possible moves that you can do. You can select option 1 or you can select option 2. So at the moment, we're here. This is where our bot is, and you can select option 1 or option 2. So how do we figure out which one you should pick? is we're going to keep looking down. So the minimax will have a depth that it searches to. So you'll keep going down the tree. So at the moment, our bot can pick one of two options. Then the person the bot is versing can pick one of two options. Then the bot can pick one or two options. Then the person the bot's versing can pick one of two options. So at the moment, this is a depth of 4 for our minimax algorithm. So right here, how this is all of the possible final board states that the minimax algorithm could end on. So here we can see, if we start in the bottom left, it's the minimizing player's turn. That means it's not our bot. So the bot is going to figure out what is the best option for the person the bot's versing to figure out. So what we're going to do is we're going to see the minimizing player is trying to select the lowest score possible. So the minimizing player would like something like -4, while our bot would like to have something high like a 9. So the minimizing player is going to pick the lowest, which would be -1. And then it's going to pick the next one along in the tree, which would be 3. And then we're going to go up the tree. And now it's the maximizing player's turn, which is our bot. So our bot wants it to be the highest value possible, which would be a 3. And we're going to keep doing it again over on this side of the tree now, which will become 8. So we know that if the bot got to this point, we'll be at 3. And at this point would be 8. So we'd kind of prefer to be here than over here at the 3, because we want to be as high up as possible in values. Then we've got the minimizing turn, and the minimizing turn is going to pick the lowest out of these two, which would be 3. And then all of a sudden we're going to do this side of the tree again. So I did all of the working out here, and the bot can do this really quickly as well, but here we can see we've now gotten up to the final node, and the final node is going to figure out which one of the two options we want to pick right now. And right now we can see our bot is trying to pick the largest option. So there's 1 or 3. Both are technically good, as you'd think of 0 as a pretty neutral number, but then we can see that if we pick 3, it'll be better for our bot, and 1 would still be pretty good for our bot, but 3 is going to be the best option. So we're going to pick 3. So we know now that our bot should be picking this option in the game. So here we go. Now we're going to go through a bit of the code. So here we've got 3 main files in this project. So we've got the main file. This will handle a lot more of the game loop and the graphics and how Pygame works. It'll initiate the bot and all of that sort of stuff. So this is our main sort of file that you actually want to run. Then we got the logic file. This will handle the actual game of Connect 4. And if you want to place a piece, you'll call this one. If you want to check if someone's won, you'll do that in this file. So this will handle a lot more of the actual Connect 4 game-based stuff and behind the scenes. And then we have our bot. This is going to be how the bot does the mini-max and calculates the best move. So what's going to happen is our main file is going to call a function over in the bot file, and it's going to call get best move. And all that the main file has to do is tell the bot what depth it wants to search to, because remember, if we look back at our presentation here, we have to pick a depth, and we don't want to go too far, otherwise it'll take way too long, because in this situation there's only 2 options, but for a Connect 4 game there's actually 7 every turn. So that gets very large, the amount of moves very quickly. So if we go back to our code, we can see we're going to call get best move, and what that's going to do is it's going to call our minimax function. Then if we go up to our minimax function, we worry about the alpha beta pruning. That is a way of speeding up the algorithm by quite a lot, but I didn't talk about it in my slides, so we'll leave it out here. Definitely a lot you can research online about that, but it's a way of speeding up the algorithm by quite a lot. We're allowing us to search to a higher depth. So what it's going to do is the minimax algorithm is actually going to create copies of itself all the way down. So we've got our first minimax algorithm that's going to get created here. Then that minimax algorithm is going to create 2 new minimax algorithms, and it's going to keep doing that all the way down. So what we can see is it's going to, first of all, in our minimax algorithm, check if we're the maximizing player or the minimizing player and run the code based on that. So let's just pretend we're the maximizing player for now, which is going to be the first move. What it's going to do is it's going to generate all of the possible moves. So I have another function that we won't really look at now, but it'll generate all the possible moves that we could do, which in most cases is going to be 7. and then it's going to loop through them. And then what that's going to do is it's going to generate a minimax function for them. And that's going to end up being a chain all the way down the bottom until the depth equals 0. So what it's going to do is it's going to get a board value returned, which is going to be our values here. So in this case, we've got up the very top, we've got 2 values that will get returned. It'll get returned 3 and it'll get returned 1. And then all this one has to do is decide which one's higher, which in this case is 3. So it's going to pick our first option. The other important fact is, where was it? It was down here. So it's going to loop through all of them, and then it's going to pick, if that board value is higher than our current value, then we're going to add it to our columns, which is what we want. The other important thing is up here, we're going to check if the depth is 0. And what we're going to do is, if the depth is 0, we're going to analyze the board. And that's how we've gotten all these starting numbers. So we're going to analyze the board, and that is going to give us the numbers that we start with. So we'll figure out if we're in this board state, we're saying that's really good for the bot. If we get to here, we'll be 5 positive, which is really good. And that's how our Connect 4 bot works as well. Or this one will be -1, which isn't so good. And so that's going to get passed all the way back up until we get to the very top. So that is the main idea. And it really just gets repeated in reverse for the minimizing player. So it's pretty simple. Lastly, I just want to show the bot a little bit in action, which is, I'm just going to run the file. So here we can see the bot. It's going to say it searched to a 5 depth in 0.085 seconds. So it did it pretty quickly. And then we can have our move, and we can just sort of verse it. Now, at this depth, I think I might be able to beat it, but I've set it to go for a bit longer, like maybe take 5 seconds a turn, and I've still not managed to beat it. So it's pretty strong at the higher level. Let's just play it out a little bit. Oh, there we go. It's 1 already. So that's the bot. You can also find all of the code on my GitHub page if you want to look at any of it. So yeah, you can look at it all you want, and there it all is. So thank you for listening.
That was very cool.
Very cool.
I'm definitely not that good at Connect 4.
I really liked the tree, the explanation of how the tree and the minimizing and maximizing work go further over. There you go. Yeah, I really like that. I thought it was a really good explanation.
Yeah, I love algorithms. They're super cool. I love seeing really practical uses of them.
Yeah. Okay, our next talk is not on my screen anymore. Is Zachary Draper and Oliver Waldock. And Zachary and Oliver have been programming for about 3 years and 1.5 years respectively. And favorite emoji on the screen. Zach has learnt that 3D printing is a lot harder and slower than it looks. And Ollie has discovered that, and I quote, working with computer vision sucks. We're going to see about logistic chains.
Logistic chains sorting system by me, Zachary Draper, and Oliver Waldock.
Our project looks at making the world a better place. Our original idea was an island under lockdown where we would send supplies and be able to retrieve and sort them and send them out to the island. Although new ideas include search and rescue applications as well as floating plastic and for collection and processing.
Right, so my part, which is the sorting system, my plan for the software is to create a color sensor, which is able to sense what sort of rubbish and or care packages come in and be able to sort it out. For this, I want to be able to create a self-learning algorithm that is able to calibrate the color sensor. Next, I want to have a button matrix interface for users to be able to control the system. I want a robotic arm which can unload the boat, which docks at the dock. For the dock, I want to be able to use electromagnets to hold onto the boat. My plan for the hardware model side is a sorting system, which is obviously using the color sensor, then the robotic arm, electromagnets to hold onto the boat, a servo board to be able to control all of my many servos through the project, and connecting this all up to an Arduino Mega.
All right, so this is the boat side of the project of the collection. My aims with this were to create using computer vision to locate the ball, locate the boat, calculate the distance between all of them, and work out the best optimal ball to target, as well as communicating that to the boat. As far as what's on the boat, it's pretty simple program, taking the input signals, interpreting that, and sending that out to the motors to execute. The hardware side of things, I need electronic capabilities to be able to move the boat forwards and backwards, as well as turning. Radio transmission between the boat and the computer vision, as well as a decent camera to pick up the specific computer vision elements. 3D printed aspects, adequate space for all electronics on board the boat, waterproofs, so leaks in the boat, as well as the ability to hold balls and a conveyor to pick up the balls.
All right, so next we're going to show off our demo of our projects so far. And now the challenges that we encountered while creating our projects so far.
One of the main issues I found into originally was how to view the whole area and locate the balls. One of the major problems originally was where the camera would be. So I thought about having two mounted cameras on the front of the boat. That way, using stereo vision, which I've done a little bit of research into, I could work out the distance to the balls as well as where they were. But it only had a limited field of view, and water is dangerous to electronics. So I thought of a drone camera, sort of a bird's eye view. I was able to have a full view of the situation, very little water risks around that, although it did mean that I needed to create the radio communication. The camera quality was another issue. In the far left, I was using a little, very old webcam that the resolution was alright for working with balls on that scale away from the camera, but when I went to a bigger scale that it would ultimately be set up in, it was too small to register, so therefore I had to get a camera with a higher resolution. We did have some radio problems too with the Raspberry Pi connecting to the Arduino. Instead, we used Raspberry Pi to Arduino and the wired with Arduino to then wirelessly connect to the other Arduino. I had bad motors and circuits. The torque on the motors wasn't quite enough to spin the propellers, so I designed these gear systems, and they've evolved over time. Originally, they were going to be held on with bolts, but I found out that friction holds work very well. We also had bad circuitry issues because I wasn't able to use soldering in the IT lab because we didn't have the ventilation facilities. Water. We did have a leak less than 24 hours ago, so lots of the demo was filmed, as you saw, not very complete. We haven't fixed this issue yet, but that's one of the main things we do need to fix.
All right, so one of our main issues when creating our projects was that we used 3D printers as our main point of hardware. And some of the issues that we ran into, as seen on the screen, is layer shifts, which you can see on the left side. And then with this turned into support structure failures, bed adhesion, as you can see in the bottom center, and then bad printer profiles causing the prints to turn out in a sub-optimal way. So a good way that the printers helped was being able to create friction fit items. As Ollie talked about earlier, the 3D prints ended up being so precise that we could just stick them together and they'd hold really well. So you can see on the left side, I created a servo mount, which would hold the servo in so well, I didn't end up needing glue. This also ended up working well for the funnel and the top of the funnel. There's about 300 grams of electromagnets hanging off the side there, and I still didn't need glue to be able to hold that onto the funnel. You can see all I had to use was the pins. All right, so another issue with this and 3D prints was I didn't realize that the square funnel would hold all the 4 balls so perfectly together in the funnel. Henceforth, I had to change to a circular funnel, which lets the balls flow very free. Next big issue that I encountered was running servos. We figured out that the PWM power supply for servos on a basic Arduino board ends up being that you can only run one, at most 2 servos off a base Arduino. Henceforth, I bought the AC adapter you can see on the right, which steps down 240 volts to 5 volts, and then puts the 1.6 amp hours up to 10 amp hour, which allows me to run up to 16 servos off the board, and then also will allow me to run another motor board to use for a stepper motor for my robotic arm next term. Color identification and then the calibration for that. I have the range of the color numbers out of the color sensor, which you can see on the left side, which I'm able to run in a color calibration code prior to be putting it into my main code. All right, buttons. I had a massive issue in my first semester when I was trying to get buttons working to be able to test the basic functions. I found out that on the right side there, the buttons were too small to be able to reach the pins in the breadboard, meaning that I had massive breakup issues and they were super unreliable. Henceforth, in the next term, I bought a little button board, as you can see in the bottom right there, which connects via a ribbon cable straight to the digital pins on my Arduino Mega. My next issue I encountered was that the electromagnets were not working sufficient to be able to grab the crate, as I'd need an arm in between the electromagnets and the crate. To fix this issue, what I decided to do was scrap the electromagnets entirely, and I'd just use the robotic arm to put the crate straight off the boat and empty the ball straight into the funnel. Right, so the future scope for this project.
All right, so what needs to happen with the boat in future is obviously we need to redo the waterproofing. That's a big issue. Calibrate the boat movement values. I was trying to do that recently, but with the boat leaking, that was made not possible. Finish off the conveyor. We're getting close, but there's still some issues that need to be resolved. Optimization of ball selection and movement of the boat, and making it return to dock so we can unload the balls.
All right, then in the sorting system, I've got to implement the self-learning color calibration for the sensor. Got to put the robot arm in to be able to unload the boat. I want to get a labeled button matrix interface so that you're able to start and stop the system. Optimize the speed so that it can go in a somewhat speedy fashion, and then put the top on my funnel so that the balls don't go everywhere when the robot arm empties it. And then, like Ollie talked about just then, we got to add a dock. So the dock is seen here, where the red circle is the electromagnet, which will attach to the back, which we will be able to attach to the back of the boat with small magnets on it to be able to hold it in a set place for the robot arm to be able to grab off every time. The black square there is the MDF board that everything is connected to on my side. Here are our references, and that's it. Thank you for listening to our presentation.
If you have any questions, come see us.
That was fantastic.
That was wild. I really liked how we saw all of the move this way, saw all of the things that they hit, the struggles that they'd had, the challenges, and then how they either planned to fix them or fix them throughout the process. That was great.
Yeah, the problem solving is so good. It's such engineering.
Yeah,
it's so good.
And important to have a hairdryer if you're going to do electronics projects with water.
Right.
Got to have a hairdryer.
Cool. So yeah, up next we have Vanessa. Vanessa's been programming since 2015, so about 7 years. Her favorite emoji is the star eyes emoji. And she recently discovered that most banana peels and sausages work on touch screens. I won't ask any other questions. So now we're going to learn about 3D Minesweeper.
What changes as a cube's perspective is altered? How can we show this on a 2D screen? These two questions underpin the production of my software design and development major work, 3D Minesweeper. Although this idea was spurred by a lack of popular sequel to the original game, Minesweeper, the project quickly became overrun with the difficulties of adding a third dimension, particularly on a 2D plane. Today I'll begin by outlining some background information as well as how I approach displaying 3D shapes. Then I'll break down 4 of the main challenges of my project: the vertical perspective change, the horizontal perspective change, cubic data structures, and teaching the computer depth. For those who don't know, Minesweeper is an iconic logic puzzle popularized in the 1990s. You may know it in its original format, or for my fellow Gen Zs as this Google version. The game takes place on a grid, representative of a minefield, in which bombs are randomly scattered. The user begins by selecting a square, revealing a cluster of numbers which indicate the amount of bombs which are present in the 8 positions surrounding the specific numbered square. Through a process of deduction, the user must figure out which squares are bombs and which aren't. In 3D Minesweeper, the minefield isn't a grid, but a cube. This is my final product. Left-clicking on a cube destroys it for kids with no surrounding bombs. Otherwise, a color representative of a number is revealed. Flagging a bomb turns this particular cube red, and the perspective of the cube is changed using the left, right, up, and down arrows. What makes this project so interesting is PyGame's incompatibility with 3D shapes. PyGame can draw a range of polygon types, from triangles to dodecahedrons, but comes nowhere near to facilitating the tools to draw a cube. As a result, 3D objects must be drawn to the screen from their 2D perspective. A 3D cube can be drawn to a 2D screen using 6 rhombuses, 1 for each face. This is the approach I took for my 3D model. This can be achieved with these variable values. dy and dx are necessary because they dictate how far from the center coordinate this top right corner is. Hence, through this approach, each corner can be calculated from the original coordinates of this top front corner. This is my first draft, experimenting with the 2D portrayal of a singular 3D cube. Using a bit of math and the previously specified dy and dx, I was able to loop this to draw the whole cube. However, if this front cube is drawn first, its surrounding cubes would overlap it. Hence, the cube with the x, y, z coordinates of 2, 2, 2 is drawn first, then 0, 0, 0 last. So, how is dx and dy calculated? These lengths are crucial to portraying a perceived change in a vertical shift. To decipher the visual differences of a vertical change in perspective, I found an online version of 3D Minesweeper and observed that the changes that occurred when the user's vertical perspective changed. What changes do you notice here? The main difference I noticed was a change in this internal angle. It becomes obtuse from a higher perspective and acute from a lower perspective. By changing this angle, the appearance of the rhombuses would change drastically. However, I needed to ensure that they maintained their rhombic nature by keeping each of the sides at a constant length. And how would you relate 3 sides and an angle? Trigonometry. For the many who haven't used high school trig since, well, high school, right angle trig relates 2 sides and an angle using these trigonometric ratios. If we draw a horizontal at this point here, a right angle triangle is formed, giving us the ability to relate this internal angle, the upper side, dy and dx. So now when the user presses the down arrow, they decrease this internal angle, and dy and dx change accordingly. With the up-down shift pretty much working, I began to suss out the horizontal shift, using lots and lots of drawing. Finally, I noticed a pattern in the change of coordinates when rotating a cube left and right. I noticed that if you look specifically at the corner coordinates, as you can see here, one pair of diagonal corners shifts vertically, whilst the other shifts horizontally. Whilst this approach quite clearly highlights the direction of movement, it doesn't address how much these coordinates need to be altered by in order to keep their proportions. To figure this out, let's consider the range of motion of each point. And now we're sketching the rhombus coordinates that we know and love. Let's focus on this back corner and assume that the cube is being rotated in a clockwise direction. When this point is at its greatest x coordinate, it is dx away from the starting coordinate. So the total horizontal length shifted will be dx. I decided that it should take 5 presses to turn an 8th rotation, as we are trying to achieve here. Since after 5 presses, this coordinate would move dx to the right, each press should shift this point 1/5 of dx horizontally. To shift the vertically moving points, a similar distance will be calculated using dy. So this is the horizontal shift so far. Following the coding of the cube's perspective changed, I added a bit more consistency in the color. Whilst this may seem like a straightforward thing to change, coding the 6 rhombuses of a cube to work together as a single object was potentially the most unforeseen challenge I faced during this project. I solved this issue using a 4-dimensional array. Often we think of an array as a single row table and a 2D array as a larger table or a sort of grid. Since 4-dimensional tables fortunately don't exist, I'll be representing this pivotal data structure using circles. My 4D array is entitled cubes and holds all the information required to draw these cubes to the screen in the main line. It works like this. Step 1. The corner points of the cube are calculated using dy and dx, as aforementioned. Step 2. 4 of these corner points are selected and grouped in an array, making a rhombus. 6 of these rhombuses are collated in an array, holding the information required to draw a singular cube. Step 3. In the main line, the cubes are drawn to the screen using 2 for loops, one to iterate through the cubes and one to iterate through each rhombus in a cube. To do this, a counter is set up. This comes in handy a little while down the line, so let's call this the cube counter. The cube counter is incremented after every cube is drawn, making it a 2D index of each cube. The fundamental component of this system is the cube counter. So, why is having an index of each cube so important? The cube counter makes sure that a rhombus isn't being treated as a rhombus, but as a face of a cube. With 6 rhombuses having the same index, they can act as one. This really comes into play when the color of the cube is being decided, particularly since color coding is such a big component of the 3D Minesweeper game. The cube's colors are predetermined, added to a one-dimensional array, and accessed using the cube counter. So, the first cube would be the first color in the colors array, and so on. The cube counter is also particularly pivotal when determining which cubes have been clicked or not. When the user selects a cube in 3D Minesweeper, they are actually selecting quite a few objects. How would the computer know which is in front? Also, remember when a cube is clicked, it becomes transparent entirely, or with an outline if there is a bomb nearby. If the user must be able to click through these transparent cubes in order to select the ones behind it. But how would this work? Would the program need some way of processing which cubes are at the front and which are at the back? In fact, they already do. Remember when calculating the rhombus coordinates, how the cube with the x, y, z coordinates of 2, 2, 2 is calculated first, and then how the cubes are sequentially added to the array of cubes? What I'm getting at is that the 4-dimensional array of cubes is already ordered from back to front. Hence, as each cube in this array is checked to determine if it was clicked, the last cube to be detected as clicked equals true is the cube at the very front. The cubes which have a transparent status are all compiled in a list. Hence, it would be easy enough to exclude the transparent cubes from this search by adding an extra condition in the if statement. This seems perfect. A 3D system relying on a one-dimensional array. What could go wrong? Unfortunately, this one-dimensional index was very unhelpful compared with the perspective change. I'll show you one example. This perspective change seems to be working fine. However, as soon as the user takes up a position from a corner that is not this top one, we have a little bit of a problem. The bottom face is overlapping lower cubes. But why is this happening? Remember how the 4-dimensional array is ordered from back to front? And this is a really great thing because that's how the cube should be drawn. When the user looks at the cube from a lower perspective, cubes is no longer ordered from back to front because the perceived change in front and back have changed. The front corner is now the bottom corner rather than the top. Hence, the drawing of the higher cubes is still prioritized over that of the lower cubes. This left me stumped. I spent weeks thinking of a solution that wasn't awkward and tedious. To solve this problem, I had to implement some kind of sort, but this became very difficult as there is no identifying feature of the cubes which highlights how close or far these cubes are, let alone a feature which is sortable. To attribute an aspect of depth to each cube, I created a sort of reference array. This was a one-dimensional array in which each object represented a cube. The position of this cube in the array adhered to the cube counter used when drawing the cubes in the main line. So the cube which is calculated first takes position 0, the cube which is calculated second takes position 1, and etc. Furthermore, the cube is represented using its x, y, and z coordinates. For example, this cube is 0 across, 0 up, and 0 deep. Hence, it can be represented in the array like this. So, now we have a one-dimensional array which mirrors the order of the array cubes. And the best part is, this reference array contains objects which are numerically sortable. When looking at the bottom corner, we want the y coordinate to be high and the x and z coordinates to be low. So, the y coordinate takes first priority and the x and z second. To sort the cubes from front to back, this array must be sorted. Then the swaps made when sorting this array will also be implemented to the cubes array. For example, let's compare the reference list on the left and the drawing array cubes on the right. Clearly, this value is higher than this, so the array positions will be swapped. This swap should be implemented in the drawing array, cubes. By the end of this sort, cubes will now also be ordered. This led me to my final product. Developing vertical perspectives, horizontal perspectives, cubic data structures, and computers' understanding of depth gave me an outcome of a strategically challenging and entertaining game. And whilst many features can be improved, I believe my product fulfills its purpose of a Minesweeper sequel. Thank you for listening.
some strong compliments on the beautiful, colourful, hand-drawn diagrams and a request for Vanessa to write a textbook on the conversion between 2D and 3D and the maths involved. Who said you didn't need trigonometry in real life?
Cool. I think you're introducing.
Yes. I have our next speaker is Patrick Reed, and he is going to be talking about extending Python with macros. Patrick has been programming for about 6 years. His favorite emoji is the box emoji because shipping products is a goal that I aspire to but never quite achieve. He's been learning all about how browser engines work, specifically Gecko.
Cool.
And
before we get on to Patrick, we have another question from the chat, which is, can people play your Minesweeper game? And if so, where?
It's currently only on Replit. It's currently only on Replit, and I don't particularly intend on posting it anywhere. I can look into putting it on GitHub, but there are also currently a couple of errors.
Yes.
That's what GitHub is for.
That's what GitHub is for. All right, queuing 6. Yep.
Python is a great programming language for scripting, experimenting, and building all sorts of applications. However, there are some language features that it doesn't have that I would absolutely love. So the question is, why can't I extend Python to add them? And how hard would it be for me to build a system for doing that? This got started after a school project where I was tasked with investigating parsers, and I wanted to try building my own programming language to solidify my knowledge. All was going well. I'd found the LLVM bindings, which would have allowed me to write higher performance machine code inside of Python. Then I found out that Python didn't support addition types. Addition types are part of an algebraic type system. Algebraic type systems can be broken down into two different subtypes: product types and addition types. Product types are already in Python. They're where you group multiple different subtypes together into one big group type. So for example, a Python class, where you can have a number of different subproperties. Addition types allow you to select between multiple different types depending on a case. The most Pythonic example that I found of this is Scala's enum types. You can select a different case, and that case can have, for example, a class attached to it. Ideally, this would be used for storing the abstract syntax tree, but Python doesn't provide a clean system for doing this, so I would have to implement it using classes, which would be messy, repetitive, and hard to read. So, rather than just dealing with it and writing messy, hard to read code, I decided I'd try and write a macro system in Python. Let's take a look at what that is in practice. The first thing I need to do is import the enum macro. Macros are a concept in several programming languages, which allows you to extend the syntax of the programming language. My concept is based on Rust procedural macros, where you can take in a string of token and output code that you want to insert back into the Rust file. Now that we can have imported the enum macro, we can use it in our code. I'm going to create one for storing several different animals. I'm going to store a cat option, I'm going to store a dog option, then I'm going to store an other option, which will take in the attribute of name, which I'm going to set to have the type of a string. I'm then going to create a cat instance and a lion instance. Because we don't have a lion on our animals class, I'm just going to use the other type for the sake of demonstration. I'm going to assert that a cat and a lion are not the same thing, which they shouldn't be. And I'm going to assert that a cat is a cat and a lion is a type of other. I'm also going to access the name on the line and print it to the console. If we run this command through macros in the command line, we can see that none of the asserts crash our program and that line is printed to the console. If we look at the generated code that came out of this file, we can see that down the bottom is our logic, so our assert statements in the print statement that we wrote before. So that's all fairly normal. However, the enum macro has been replaced by a number of different classes to represent each type and a bit of glue that will mix them all together. Doesn't really matter what this code does, just that it works and that it was generated. Under the hood, my program breaks the file down into tokens, which are the computer equivalent of words. It then looks for specific trigger tokens, so enum or macro. Here we're looking at enum. It will then start sending all of the rest of the tokens for the file off into the macro parser, where it will parse it and it'll try and construct it into a structure similar to how humans read it. This process is the most complex and it needs to be written custom for each macro. I've chosen to go with a recursive descent parser, which starts with the first token and then tries to match each successive token with a list of different patterns. And that's how it builds up its data type. This is good because it's fast, it's fairly easy to do decent error reporting, and especially important for me, it's really flexible and it can be dumped in a place and end before the end of the file. The parser will return an abstract syntax tree. At the top of the tree, there'll be an enum, which makes sense. This is the enum macro, which will have the name, in this case, animals. There'll also be a list of options, for example, cat, dog, or other. The other option will be able to take in a number of arguments, in this case, one with the name of name and with a string type. The tree is converted into Python code using a number of functions, which there's one for each subset of this tree. This Python representation is then replaced over the original macro in the Python file. There are, of course, plenty of places where this can go wrong. For example, if you enclose a macro in a function, originally it would not indent it, which means you get indentation errors. To fix this, I had to make sure I made a note of what the current indentation was when I started parsing a macro and just append that indentation to the macro later. I also didn't really know how I originally wanted to structure this. I originally planned on using, for example, the untokenized function to convert a list of tokens returned by the parser into pretty printed Python code. The problem with this is that the Python untokenizer is really strict and it expects that all of your tokens are in the correct order so that they're correctly formatted and everything's nice and clean. However, because we're generating custom macros, the lines are not in order because one line may map to several lines of a macro. So I just discarded this idea because it was too much effort and the output is just messy to this day. If you remember how at the start, I mentioned that I was trying to solve a problem, which was that making abstract syntax trees was messy within Python. But because I'm writing parsers, I need to write abstract syntax trees, which are messy because I haven't written the parser for the thing I need it to. So the solution to this was something that I came across whilst researching for writing my own compiler, which is this idea of bootstrapping. You write a basic compiler that's on a different system or that's in machine code that can compile a very minimal example of your language. And then you start writing your parser in that minimal example, and you build up a more and more complex language over time that's more and more powerful. I used a similar idea. We have one base macro, which is the enum macro, and then additional macros are parsed through the parser, which allows them to use the enum macro and build on top of it, making their code cleaner, even though the enum macro's code is still messy. But not everything has been nicely ironed out. Currently, I'm using the Python syntax highlighter to highlight all of my code in my examples and when I'm writing code in this language. But that highlighting doesn't take into account custom tokens, for example, macro or enum. The current solution to this is that I'm just dealing with it. But it gets worse because I can't enable language servers, which provide context-specific autocomplete. The reason for this is that if I enable one, I get an enormous number of errors, which are just painful to work through, and I don't want to have to deal with. I could fix this problem by writing a custom language server, but writing language servers is a task that can take months or even years, and I don't want to add that extra time to this project. I want to get it done and get onto what I want to do otherwise. So I've just gone to live with poor autocompletion and bad syntax highlighting, and I'm just dealing. However, at least I can now use addition types in Python and get back to the thing I originally wanted to do before I started this multi-month tangent, which is experimenting with LLVM, recursive descent parsers, and Python. If you want to check this out for yourself or look into any of the specifics of my implementation, you can look at the GitHub repo that's currently on screen. Otherwise, you can grab it from PyPy if you want to play around with it. Otherwise, have a great day.
Well, that was very cool. Learned a lot about Python that I didn't know before, which is very fun. Yeah, I feel like it's a very common developer thing to get onto a massive tangent and then
really
go,
big tangent. Yeah.
like a week later.
I'm just going to write a parser.
Yeah,
I do that all the time.
Constantly writing parsers, me. Yeah, that was very cool. I think Patrick is online, so if anybody has any questions, I think we can pass it through.
Also, we have Zach and Ollie online, who were the boat and the sorting balls logistics thing.
Yeah. Cool. So up next, we have Sam Hogan. Sam. Lots of fans in the audience. Sam has been programming for 10 years. His favorite emoji is this one, which I shan't describe. And he has recently started learning some basic Rust and is only slightly dying, in his words. So we have a look at Sam's.
Hey everybody, I'm Sam. I go by Official Death online, and today I'm going to be doing a talk for you about curvy maths. A while ago, I was trawling the depths of YouTube when I found this video by Freya Holmer. It has a somewhat simultaneously succinct and in-depth explanation of Bezier curves, with the maths being relatively simple and the graphics being simply beautiful. It inspired me to create a program. So, what is a Bezier curve? Well, paraphrasing Wikipedia, a Bezier curve is a parametric curve, defined by a set of control points. But what the heck does that mean? Well, you might have seen a form of Bezier curve already. If you've ever used a vector tool like Adobe Illustrator or Figma to create any art, or any other of a massive range of programs, from animation to 3D modeling, they're absolutely everywhere. But what do those weird points that change the curve even mean? Well, behind the scenes, there's a surprisingly simple algorithm going on. To draw the line, the algorithm basically connects a bunch of tiny points, determined by the percentage they are along the original lines. For example, at 20%, the algorithm looks at 20% along the first line, and then on the second, and so on. It then connects those points with the lines, here in blue, and puts a point on those lines the same percentage along. If you can see, here is 1. It then repeats that process until we get to the final point, here in red. Do that for as many or as few percentages as you want, and you get something that looks like this, a nice little curve. But this got me thinking, right? If the algorithm already goes from 3 lines to 2 to 1 to none, maybe I can make it do wacky stuff by adding more lines. And with that thought, this project was born. Just to rush something out as quick as I could, I started by creating a little prototype using JavaScript and an SVG canvas, which let me do a few simple things. First of all, clicking to input points. That was really useful. And having a slider to choose what percentage to look at. This is a budgy hodgepodge of features that I added as I thought of them. Dumbass mode, which changes from the base 60 total frames, I don't know why I chose 60, to 1200. Random weird numbers, I know, but this basically increases the precision of the line. And chaos mode, which on top of drawing a trail for the main dot, draws a trail for every dot that moves. It's a bit crazy. Those look relatively normal to you though, don't they? Well, it starts to get there, as you'll see soon. You see, those don't change much when you're doing something as simple as 4 points, but the complexity increases at an ever-increasing rate with each line you add. So you have to be kind of reasonable with the kind of patterns you give the... Okay, so hear me out. The patterns make the funny colors, and they look nice. So, jokes aside, I basically immediately implemented a way for me to generate interesting patterns to make my PC chug. Hey, how did that get there? We're here for pretty colors and maths, not benchmarking. I wanted to make pretty things with this interesting maths. So I coded myself a bunch of little Python functions that I just jank into the page before it runs. From a zigzag, to this cool curve, to that scary box from before. So where on earth is the Python? Well, there are 2 main problems with the current solution. 1, the main drawer of these renders is actually watching the pretty colors move, and there's simply no way to share a GIF of a JavaScript canvas to my friends. And 2, it's so hecking slow. I just timed how long it took between frames for the box on the last slide, and it was a whole 11 seconds on normal mode. Here's where Python comes in. I already have some cursory knowledge of SVGs, so I decided to make a Python file to render out each frame as an SVG. Not only was this far faster, I know, Python beating anything at speed, shocking. But now, I actually have each frame as an infinitely detailed SVG. I did exactly the same test, the box for 60 frames, and it took the same amount of time as a single frame. And on top of that time, I can make this sick GIF from the frames using 2 online tools. This is that box with 60 frames of precision, which admittedly looks like a bit of a mess, right? So I wasn't quite satisfied with using 2 different websites to make my GIFs. The SVG convert one has a limit of 20 per conversion, and overall the process was pretty slow and it looked kind of bad. Well, what can you do, right? It turns out there was something I could do. I graduated from manually uploading to 2 websites to using Python to do all that conversion automatically. Here we have the first 2 things I created using command line tools. Inkscape to convert from SVGs to PNGs, and then the Linux convert command to take those PNGs and create a GIF. You can see the first one is the same test as before, though the detail in this one is far greater. And the second one is a render of the zigzag, which I think is one of my favorite patterns to watch. This is all I had time for in this presentation, but by the time you see this, there will be more examples on GitHub. Well, everyone, that's all I have for you today. I hope it's been educational and at least a little bit entertaining. Both these slides and my code can be found at the GitHub link on screen, and I hope you enjoy the rest of your showcase.
Well, we started with pretty math and we ended with pretty math, so that seems pretty good. I loved the GIFs. Good job, Sam. We do have Sam here if anyone has any questions for Sam, either in chat or in the room.
Yep.
We'll give it 7 seconds. The official waiting period of this event.
Okay. Well, that is the completion of the student showcase. So round of applause for everyone again. We have Renee, who's going to be giving about a 10-minute talk now about, well, actually, I'll leave it for her to tell you. But then we're hoping to run Jack's talk again so that we can see it in its entirety. It's just the online crew have already seen it 1.5 times, and we'd rather just leave it till after Renee's talk. So I have a quick intro for Renee. Renee Noble has been a full-stack developer for a while now and is passionate about teaching technology to students and adults alike. She works at Microsoft, is the executive director of Tech Inc. and Girls Programming Network, as well as running a startup called Connected Code. How does she fit it all in? Thank you very much, Renee.
Thank you, Amanda. I'm just working with my lapel mic, so just for less confusion, I changed shirts, so you know I've changed personas. You did miss one thing. I also teach Year 10 at Presbyterian Ladies College, which is, you know, kind of where it fits into this talk, solving the mystery of getting kids into coding. Obviously, we're not talking about any of the kids that's presented today because they're all amazing and they're, you know, probably even more into coding than I am potentially. And you just heard my list of stuff. But yeah, the mystery is many schools struggle with getting kids into coding because there's a lot of difficulties. Like, it's been added to the national curriculum in the past 5 years, but there's sometimes just not enough time in the curriculum. There's lots of stuff, other stuff to do. Schools have a lot of stuff going on. And it's like, well, where are we going to fit this in? You know, we've got all these other classes going on and we need to do some textiles and we need to 3D print something. And where are we going to fit in the coding? Or sometimes there's just not teachers available at the school that know coding because, you know, 5 years ago, we decided that teachers need to know coding to teach it to the kids, but then no one could teach the teachers. And people have tried, but it's really hard. And some schools are lucky to have amazing teachers, like a lot of the kids in the showcase today, like Amanda. So that's fantastic. But a lot of schools are still like, how are we going to get all the kids coding and make sure they're ready for the digital future? So yeah, a few years ago I was going, you know what is great? The Girls Programming Network, as you know, Alex and Amanda are nodding in the front, and lots of people have come to the Girls Programming Network. And as you heard, Amanda listed that deeply involved with GPN for quite a while. And if you haven't heard of it, we teach girls to code across the country by women and gender diverse people for girls and gender diverse kids with these free workshops. And then mid-COVID, like lockdown, so that's when you have like your deepest thoughts and you go, maybe I should like do something different with my life. And I was like, you know, it's really good, GPN. We should like have that kind of stuff for schools so everyone can have that cool experience because the girls come and have a great time and then they do coding. What if everyone was that excited about coding? So I went, okay, maybe there's something that I could do because I have developed all these like resources and skills and contacts and stuff. And then I was like, I'm going to do this thing, and it's connected code. So yeah, mid 2020, I quit my job and I started a business, which is probably not a normal time to do that. I don't know, but it was fun and I'm here now. And yeah, so I decided I was going to connect coding with context, community, and curriculum. And so yeah, that kind of this is my first clue on my adventure. So I was like, okay, I'm going to do that, but like, how am I going to start doing it? I guess I kind of got a year before I run out of money. So we're going to make something work. So I was doing some consulting for the OzSTEM Foundation, who make a very cool thing called the Kookaberry, which is a lot like a microbit, but I'm going to say even better. We've got this really cool display. We can print text on it, which makes debugging really easy. Or if you just want to make like a little Tamagotchi, you got a whole screen there. You also got 4 buttons, and on the back you can plug in a lot of different stuff. So I was like, this is really cool. And at first, like, I didn't know what to do with it. And I actually spoke about this at PyCon AU last year about like, I was trying to do microbit stuff with it, but then I've discovered there were so many more possibilities to think of. Because if you know me at all, you know that I like to think of the stupidest thing I can do that's over-engineered and go, this is going to be so exciting for the kids. We have to do this, everybody. And then we managed to do it by sleeping less, but it's really great at the end. So that's kind of the start of my business. So I made things like this Play-Doh xylophone. It actually makes sound, which is very cool. Or this piano that's made out of paper. These are all powered by the Kookaberry, and they actually make music. Or the piece de resistance, which is the giant piano. So yeah, and the kids actually got to wire the circuits underneath this, connected to the Kookaberry, and every kid got to program a note. So they learned how, PWM works and things. And these kids are like in year 2 to 6. So everyone with block coding can learn how PWM works and make circuits make sounds. Let's see if the sound will actually play through on this one. Yeah, so as I said, it truly works with this beautiful song that the children have played for us just now. Let's not play that again. But here's where the light bulb moment kind of came in. So I've been, as I said, I work at PLC Sydney teaching Year 10 computer science, and that was actually their gifted and talented program for the weekend where kids from any school can come along and do this. So I got a lot of opportunities to do some experiments on children through PLC Sydney because they're really excited about technology. So yeah, the principal came to me and was like, I want to run a really good tech event. I was like, tell me more. This is what my business was kind of made for. I'm not sure if you fully understand that, but yeah, I'm here for all of this. It's going to be awesome. So the light bulb moment was I needed to murder the school librarian. And that's how we were going to get all of year 7 at once excited about coding. And we did. So I ran a 3-day school incursion with the help of about 25 lovely tutors who came and worked for me for 3 days, whether they were some of them in this room and took the day off work from their high-paying tech jobs, and lots of them were uni students who were very excited to get people into coding. So yeah, they joined us, and we took 185 girls in year 7, lots of who had done no coding, some had done block coding, and a couple had done some Python coding, and we taught them all how to code Kookaberries with Python to make their own detective tools. So we're making moisture sensors to test if the moisture of the soil under this car spot was very wet, because we know that it was raining at the time of the murder. So was the car there or was it not? We're making all these detective tools. We're cracking ciphers for all these mysterious notes that appeared around the school. We're gathering data about the location of teachers using altitude sensors that we've coded up. And we're solving the mystery of all these weird, scribblings across the school. And ultimately, yeah, they solved the mystery. And obviously, it was the deputy principal who murdered the librarian to avoid paying those library fines. So that's how, I'm teaching kids to code using murder mysteries. And yeah, solving the mystery of how to get kids excited about coding and actually giving them tangible skills that are practical, because these are all Cookaberries are really great at prototyping things that you'd actually kind of build in real life. That brings us to the next thing we're doing. So this is kind of part of a two-part package. So year 7 gets to solve the murder mysteries and to do half of the school curriculum, and in year 8 you follow on and you do nearly the other half of the school curriculum by designing an escape room and making your own user interfaces. Who says user interfaces are only websites and apps? Why could they not be a cardboard box with a little Kookaberry taped into it, I think. So yeah, we'll be doing design thinking processes and creating inputs and outputs and sequences of hidden messages using data representation and binary numbers and all kinds of things, and then gluing it to a bunch of stuff to make it Alice in Wonderland themed or space themed or something really exciting, and getting the kids to work together on a project. That is really kind of how the real world works together in code. So yeah, as I said, we're doing actually the school stuff. It's not all just fun and games. It's actually doing the curriculum with super exciting, fun 3-day incursions that get kids excited about coding. So I'm really excited for escape rooms, which is coming up in the near future. I'm excited to have pictures of various, themed rooms to share at the next time we all talk about Python. But yeah, that's what I'm doing to get kids excited about coding. And if you are keen or you have feedback or you're like, you know what you should do, Renee, you should do a school incursion about this, do let me know. And I'm on all the places and you can talk to me anytime because I love friendship. Okie dokie.
Talk 1, don't do crimes. Talk 2, I love friendship. That's our takeaways today. I think that's all we have. We are going to play, I think, Jack's video again.
I have some slides just with some fun links if people are interested in more Reactor events. Yeah. So back to my other persona where, look, I'm in this shirt again. It's fine. It's okay. I'll just put this down because that looks ridiculous. But I am Reactor Renee again, and we've got a bunch of stuff, including Amanda, who's on this month's series of In the Code Garden, where we do how to get started with various technologies from scratch. This month, we're building
GitHub.
a GitHub
portfolios. Super fun.
Yeah, so GitHub pages for portfolios. You can have a portfolio in just an hour.
In just an hour.
It's amazing. So we got that. You can also go back and watch previous episodes of In the Code Garden to get started with Python. If you thought all of these students were amazing and you're like, I wish I was like them, and you're like, but I'm just starting, you can watch some of those or get started with data science, get started with front-end or full stack development, or watch my other weird series like when I just did a month on doing stuff with Wordle. I made a Wordle game, what did I do? Data science for Wordle, as well as using natural language processing and The Simpsons to make your Wordle bot better. It works, I promise. So there's various things like that that you might want to join in on. You can jump onto my website to sign up for this next Tuesday's second episode of how to make a GitHub portfolio, or watch various YouTube videos. We're at this event, so that doesn't need to be there. And here is what you probably do really want to go to. It's 3 hours of student content. It's the Asia Pacific instance of the Global Student Summit. It has 3 hours of stuff perfect for uni students, but also if you're about to go to uni as well, join us for some workshops on how to deploy something on Azure, careers panels, local founders telling you about their cool story and how they got involved with Microsoft Founders Hub, doing some design thinking, and possibly getting yourself into the Imagine Cup competition, which is really cool. And you can also win $100,000 and mentoring with the CEO of Microsoft. So why not do that? And then all this is where you can join the Reactor, catch all the YouTube videos, sign up for talks from Australia and around the world, because there's 10 more of me globally doing this. So find other people who are as excited about technology as me. So yeah, that's all I've got for you today.
Great, that's all I've got.
Yay!
Thanks, Renee. So we are going to run Jack's video again.
Yeah, so we'll just end the stream. Thank you for everyone who's joined us online. And I hope Sarah has dropped some links in the chat for you about upcoming things. But if not, she will drop them in there shortly. Yeah, there is probably a survey in there as well. And we love it when people do our surveys, because we don't know what to do more of in the future and what you like. But thank you for everyone coming online.
One thing before we go, next time you see the Student Showcase, it will be live and at PyCon in Adelaide for 2023. So if you're not in Year 12 and you're super keen to try and get into the Student Showcase again next year, there might be some travel involved, which would be super good.
Yay!
Yay.
Awesome. I'll just check back on our stream to see that we're no longer live. We are infinite. Infinitely streaming, potentially. I'm going to end our broadcast. Thank you, everybody online. Catch you at the next Reactor event.